So eventually we actually more than this, less than or equal to the dimension of x, excuse me. So the idea is we just keep trading everything up until all these cells are in a band of a chain complex of with just two entries in it. Until, let me write this down. So we've simple homotopy equivalence x into x prime, where this is just y union some collection of n+1 cells and some collection of n+2 cells. And so this relative chain complex is just has terms in these two dimensions. So we get Cn+2 to Cn+1. Well, the point was that these were finite, so eventually you reach the top of the chain, and if you're trading everything up, depending on whether it was odd or even, you're going to end up with all the cells in one odd dimension and then an adjacent even dimension. So looking like this. And we know that the homology of this chain complex has to be 0, and in particular this chain complex being chain contractible is the same as this map here being an isomorphism. So let's finish this off. Now we assume that the torsion of the pair x and y was 0. We saw from the forward direction that simple homotopy equivalence between x and x prime doesn't change this torsion. So we know that the torsion of x prime with y is also 0. And so we can write this as a product of elementary matrices. Well, this is going to be this boundary map here, the n+2. Well, this is after stabilizing as necessary. In fact, this product of elementary matrices gives us a recipe for how to obtain y from x prime via elementary expansions and collapses. and all these cells were in x prime minus y, so all these expansions and contractions are rel y. So this is like I say, this is just a sketch of what's going on. And so that's more or less the end. Just final remark. Is another way to think of simple homotopy equivalence. So this is a corollary of the s-cobordism theorem and this discussion. Two finite CW complexes have the same simple homotopy type if and only if they have, well, I'm going to write PL for the time being, and think in a moment. PL homeomorphic closed regular neighborhoods in some Euclidean space. So what I mean is, if you have two simple homotopy equivalent spaces, then you fatten them up slightly, then they should be homeomorphic. This is roughly what it means to be simple homotopy equivalent. And there's a proof of this, which I saw in CF, the handbook of K-theory, volume 1, page 593, and it says, without loss of generality, if we have x simple homotopy equivalent to x prime, we can we can think of this as the inclusion of one end of a mapping cylinder. Then we take regular neighborhoods in Rn for n big enough, certainly bigger than or equal to 5, so we can apply the s-cobordism theorem. I mean 6? Oh, yeah, I mean 6, because the cobordism has to be in dimension 6 or higher, and of the mapping cylinder. And the point is that this should give, this regular neighborhood should be a proper h-cobordism between a regular neighborhood of this and a regular neighborhood of that. And in fact, because this is a simple homotopy equivalent, it's an s-cobordism. It has torsion 0, and then we can apply the s-cobordism theorem to say that this is a product. So in particular, they are homeomorphic, or so the neighborhoods are. Yes, so that's everything I wanted to cover in the lecture.